All right, so in this video, what we're going to go over is 7.5 and 7.6 problems. And this is the Chapter 7 review. Okay, and number 7 is going to go over the main concept of 7.5. The main idea with 7.5 is how do we graph inequalities, right? Graphing inequalities is very similar to graphing equations, but our solution looks a little bit different. Essentially, our solution turns out to be a shaded region, not just a line, right? And again, that shaded region is going to represent all the possible coordinate points that make this inequality true. If you want to see more of the theory behind of why it's a shaded region, please watch the 7.5 instructional video again. I'm not going to go over much theory in this video. Rather, I'm just going to show you how do you physically solve the problem. So we learned in 7.5, how do we graph an inequality? Well, in order to apply kind of our rules, or where do we shade, is the line solid or dashed, we need to get our inequality into slope-intercept form, which means we need to get y isolated. In order to do that, I'm going to subtract 6x from both sides. And then to get y isolated, I'm going to divide everything by -3. When I divide by a negative, as we learned way back in Chapter 3, when you divide everything, both sides, by a negative, or multiply both sides by a negative, you must flip your inequality. Okay, not because there's a -6 there, but because the value I'm dividing by is negative. And I got to make sure that when I divide by -3, I don't just divide the 12 or the -6, but I divide both of them. So I get -4 plus 2x, okay? And really all I've done is I've transitioned my inequality from standard form to slope-intercept, which allows me now to graph it. So to do that, now that it's in slope-intercept, I go down 4, I'm going to go up 2 over 1. Up 2 over 1, up 2 over 1. And I am not going to put a solid or a line yet because I need to make sure, right? The whole idea with creating a graph is to illustrate all the potential solutions. I don't know if these points on this line will make the inequality true. So how do I determine whether I make a dashed line indicating that this boundary, right? What I'm doing right now is I'm graphing the line y equals -4 plus 2x because it'll be the boundary for my region of all the solutions. How do I decide if this boundary makes the inequality true? Well, you could plug values in on your boundary, but the shortcut is to look and see if your inequality has an equal sign. If your inequality has an equal to sign, then, this little line under here, then your boundary points on the boundary will make your inequality true, and we want to indicate that by making a solid line. If there was not an equal to there, this would not be a solid black line running through the boundary points, but rather it would be a dashed line indicating, hey, the line y equals -4 plus 2x is the boundary, but points on the boundary do not make the inequality true. From there, the last step, now that I've got a boundary, I've got a solid line, is to indicate all the potential solutions by shading the region, right? The line just talks about the points on y equals -4 plus 2x, but we don't want to just equal -4 plus 2x. We want all of the area where the y values are bigger, okay, where all the y values are bigger. Well, the y values are bigger. That should indicate to us that we want to shade above the line. And again, if any of this is confusing or really, really foreign to you, these steps, you're like, why are you shading above the line? That doesn't make sense to me. Again, I would ask you to consult the 7.5 instructional video. But this is how we graph the inequality, really 3 steps. Number 1, we turn it into slope-intercept. Well, 4 steps. Number 1, we turn any inequality we want to graph into slope-intercept form. Number 2, we treat it as an equation and plot the boundary of our shaded region. Number 3, we determine if we should include the boundary. If there is an equal to sign, our boundary line will be solid. If there is not an equal to, that means points on our boundary line will not make the inequality true. So we put a dashed boundary. And then finally, to indicate all the potential solutions that make the inequality true, we will either shade above the boundary or below the boundary. And this is determined by what way the sign is facing. If the open side is facing the y, we will always shade above the boundary. If the open side is facing not the y, we will shade below the boundary. So what does 7.6 look like? Well, 7.6 is the exact same thing as 7.5, just instead of one inequality, we have multiple. 7.5 is graphing linear inequalities. 7.6 is graphing systems of linear inequalities, which are multiple, essentially graphing multiple inequalities. And so I have two inequalities here, and I'm supposed to shade the region representing all the potential solutions. Now, what's nice for me is both these inequalities are already in slope-intercept form, so I can go ahead and graph them. I don't need to transition them like I did the last one. Again, if you're not understanding why I'm doing what I'm doing, I would encourage you to consult the 7.5 and 7.6 instructional videos. So for my first inequality, it has a y-intercept of -2. The slope is 2, so I'm going up 2 over 1, up 2 over 1. Now there is no equal to here, so while these points represent the boundary, this boundary is going to be dashed. Because points, without there being an equal to symbol, points on the boundary will not make the inequality true. Okay, so while essentially we just graph the boundary of this inequality by graphing y equals 2x minus 2, points on that line do not make that inequality true. So we will put a dashed line through our boundary. It indicates where the boundary is, but also indicates, hey, points on the boundary don't make the inequality true. Finally, we will determine whether we shade above or below. And in this example, we want to shade above, okay? Because the open side of the inequality is facing the y. Now we're going to graph our other one. My y-intercept is 8. 1, 2, 3, 4, 5, 6, 7, 8. My slope is -2/3, so I go down 2 over 3, down 2 over 3, down 2 over 3. This does have an equal to, so the boundary will be marked with a solid line, indicating points on the boundary make the inequality true. And in this case, the open side of the inequality is facing away from the y, indicating we want to shade below the line. And so we do just that. In your shaded region, that will be the solution, will be this area that got shaded twice, right? Just like when we were graphing systems of equations and where they intersected, the point that got hit twice was the solution to the equations. Area that gets shaded twice are all the potential solutions to the system of inequalities, right? I don't want the area that just got shaded once, okay, because that means those coordinate points only make one inequality true. I certainly don't want the area that isn't shaded at all. That means those coordinate points make no inequalities true. But I want the double shaded region, which I've outlined here in red. That indicates all points inside that where they both got shaded. Any coordinate point there will make both inequalities true. Let's go through one more problem. And this is an application of 7.6, okay? An application of 7.6. So Mrs. Paulson bought chicken wire to surround the perimeter of her rectangular garden. She is restricted to no more than 20 feet in width. She wants to use at most 100 feet of chicken wire. Let x equal the length and y equal the width. We want to write a system of inequalities to describe the situation. We want to graph the inequalities and list several possible solutions for the length and width of her garden. And that's all we're asked to do. So first things first, let's write a system of inequalities, right? This is kind of like 7.4. Before we eliminate and substitute, we have to come up with the equations, kind of the same idea here. So here I need to come up with a system of inequalities before I graph them. Well, when I read the problem, she's restricted to no more than 20 feet in width. So W and 20, and the open side will face the 20 and will include an equal to. Why? Well, the open side faces the 20. The open side always faces what's bigger. This indicates that the width can be any value that is under 20, okay? Any value that is under or equal to 20, right? If you say no more than 20, you can have 20 and still be good. She also says she only wants to use at most 100 feet of chicken wire, which again indicates to me we're going to have an open side of the inequality facing the 100 with an equal to. At most 100 feet of chicken wire. We can equal 100, but we can't go over it. And she wants to, what is she using that 100 feet of chicken wire for? Well, we got to go back to the first sentence. She's making a perimeter of a rectangular garden. So she only has 100 feet to make this perimeter. Well, what's the perimeter of a rectangle? 2w plus 2l. That comes from the idea that a rectangle has two widths and two lengths, if we think about the different sides of a rectangle. Now, while we have come up with the system of inequalities, it's not in a great shape to graph. We don't really graph W's and L's, but they do tell us here that X is the length and Y is the width. So I can rewrite my inequalities with Y going in for W and X going in for L. And now I'm starting to look in a place where I'm like, hey, I can graph this. Okay? Y is less than or equal to 20. That is already in slope-intercept form, ready to be graphed. Remember, to graph inequalities, we need Y to be by itself. But in this other inequality, Y is not by itself. So I need to get Y by itself. Notice I am not flipping the sign here because the number 2 that I divided both sides by is positive. And I end up with this inequality. So maybe I'll pause at this moment and give you a rundown of what we've done. We were supposed to write a system of inequalities, which we used the paragraph above to do. Email me if that's confusing to you, right? If you're like, where in the world did you get those from? Go ahead and email me. From there, we're looking to graph the inequalities. And so we substituted Y in for W and X in for L, like we were instructed to do. Now we're getting them into slope-intercept form in order that I may graph these inequalities. We want to get inequalities into slope-intercept before we graph them. And now we're to a place, now that they're in a slope-intercept, that we can go ahead and graph them. And based on the values I'm seeing in my inequalities, I think a good scale would be to go up by tens. And if we graph this first one, I'll do it in blue, right? Really what we're graphing here is the boundary to start, and that would be Y equals 20 would be our boundary, okay? Well, when we have Y and just a number, we learned in chapter 6 that produces a horizontal line. Well, you'll notice I'm not going to extend beyond the axes. I'm not going to extend beyond the axes to the left because that would indicate negative x values, and x is our length, so we can't have negative length. I put a solid line because there is an equal to with my inequality, which we discussed earlier. And the open side is facing away from the y, so I will shade below. We'll graph this other one in red. Y-intercept at 50. Now, upon looking at this, the slope it tells me to use would be negative x, which is negative 1 in front of the x is the coefficient. So we would go down 1 over 1. But that doesn't really look nice when my y scale is going by tens. So I don't want to make a million little dots. So instead what I'll do is I will rewrite this slope, and I will rewrite it as 10 over 10. Why am I doing that? Well, I don't need to make a million little dots now, and it will give me a better depiction of what we're looking at for the boundary of the inequality, and I didn't fundamentally change my slope. Negative 10 divided by 10 is negative 1. The slope is still the same, but instead of going down 1 over 1, I'm going to go down 10 over 10. It's going to create the same boundary line, but I'm just taking bigger leaps, and it makes my graph look a little nicer. Sometimes you have to do that in these real-world problems. If that's confusing to you, again, come see me. So I'm going to go down 10 over 10. And I need to indicate my change in scale, right? I'm not only going up by tens, but I'm going over by tens now. Down 10 over 10. And again, notice that this boundary, I'm not extending beyond the y-axis because, again, we can't have negative width. I will make a solid line here, a nice solid line. I know I extended a little beyond the axes, but that was an accident.